Hello everyone and welcome to the second exercise from our signal theory class. In this exercise we will practice the Fourier series. The first problem is, find the Fourier series, amplitude spectrum and the phase spectrum of the following signal. The signal is equal to 2 in the interval from 0 to t over 2, and then it is 0 in the interval from t over 2 to t. Moreover, the signal repeats itself with the period of t. So this is the definition of a single period, and here we are saying that the signal is periodic. Now, each time you analyze a signal, be that on paper or in Matlab, the first step should be that you try to plot it. So here it is. The signal is supposed to be 2 in this interval, that is this part. Then the signal is supposed to be 0 in this interval, that is this part. And the signal is periodic with the period of t, so this is the period and that will repeat itself. Now to find the Fourier series and the spectra, I will first find the coefficients of the Fourier series, the complex spectrum. That is computed using this formula. In this formula, I should integrate from 0 to t, and I will be integrating my signal multiplied by this complex exponential. Before I will start evaluating this integral, I will check the plot that I have so wisely done. And in this plot, I will see that in the interval from 0 to t, my signal is 0 from t over 2 to t. So I do not need to integrate in this interval because in this interval, this expression is 0. I need to integrate only from 0 to t over 2, where my signal is equal to 2. So I can rewrite this integral into this form. I'm integrating from 0 to t over 2 and my signal is 2. This integral is very easy to evaluate. It is this. The only thing I need to be cautious about is dividing by this k. I cannot do that when k is equal to 0. Thus, this is valid only for k different from 0. We will need to treat the case where k is equal to 0 separately. But first let's evaluate this case. Here this t and this t will cancel each other out and I can rewrite this expression in this way. Here in this exponent I have a 0, so this exponential will become 1. Here a whole bunch of stuff will cancel each other out and I will be left with e to the minus j pi k. That is equal to minus 1 to the power of k. If it is still a mystery to you how I get from here to here, I have spelled it out here. So I start with e to the minus j pi k, which I can rewrite like this. Then I need to realize that e to the minus j pi is minus 1, and that will give me this, which I have here. Now, this expression will be equal to 2 when k is odd, so for k odd, this will be equal to this. And this expression will be equal to 0 when k is even, so for k even, this whole thing will be 0. So these are the values of the coefficients of the complex Fourier series, the values of the complex spectrum, but only for the case when k is different from 0. When k is equal to 0, that is when I'm looking for the coefficient c sub 0. Based on what I told you in the lecture, I need to evaluate this integral, which is actually the average of my signal. You can actually crunch this integral and do it analytically, but just by looking at this signal, it is pretty obvious that the average is 1. So the coefficient c sub 0 will be equal to 1. Now I can take these coefficients and this coefficient and substitute them into the Fourier series of my signal. When I take this coefficient and substitute it here, I will get this. I need to be cautious. This coefficient is valid only for k which are different from 0. So here I need to indicate that. And this coefficient I will need to add separately. I'm doing that here. So this entire expression is the Fourier series of my signal. This is a series of complex exponentials, which when I sum, I will get my signal. Now, what about the amplitude spectrum and the phase spectrum? Well, the amplitude spectrum is the absolute value of the complex spectrum. That is the absolute value of these coefficients and this coefficient. So starting from here, the absolute value of this expression is this. So for k odd, the amplitude spectrum will be this. Then the absolute value of 0 is 0. So for k even and different from 0, the amplitude spectrum will be 0. And for k is equal to 0, I need to use this number, the absolute value of which is 1. So this will be the amplitude spectrum of my signal. I have plotted it here. Now what about the phase spectrum? The phase spectrum will be the phase of these coefficients and this coefficient. First, this coefficient has the phase of 0. Thus, when k is equal to 0, the phase spectrum will be 0. Now, these coefficients. 0 can have any phase. I can assign any phase to 0 and that complex number will still be 0. Now, the phase of this complex number will be given by this j and by the sign of this k. When this k is positive, I have 1 over j here, and that will give me the phase of minus pi over 2. So when k is positive, the phase of this expression is minus pi over 2. For the sake of simplicity, when k is positive, I will also assign that phase of minus pi over 2 to this 0. And that will give me this. When k is positive, my phase spectrum will be minus pi over 2. Now, when k is negative, the phase of this j will flip and the phase of the entire expression will be pi over 2. When k is negative, the phase of this entire expression is pi over 2. For the sake of simplicity, when k is negative, I will also assign that phase pi over 2 to this 0. So, when k is negative, my phase spectrum will be pi over 2. When I put it all together, this will be the expression for the phase spectrum of my signal. I have plotted it here. Here I have a similar plot that I showed you on the lecture. In the lecture, I told you that when I combine a complex exponential for some k with a complex exponential for the same negative k, the combination of these two exponentials will give me some amplitude scaled and phase shifted cosine. When I do it for this signal, that is for these complex coefficients, I will get this for k1 and minus 1. And I will get this for k3 and minus 3. I will get this for k5 and minus 5, and this for k7 and minus 7. Also for k is equal to 0, I have this number 1, that is this constant. So this is actually the average value of the signal, this is the fundamental or the fundamental harmonic, and these are the higher harmonics. Now when I add this average value, this fundamental and these higher harmonics, I will get this. So you can see that when I add only these first 5 signals, the sum already starts to resemble my signal. Of course, the fit is not perfect, but for that I would need to add that infinite number of the remaining higher harmonics. Last, you should note that this amplitude spectrum actually gives you the information about the amplitude of these tones, of these harmonics. This value, which is 1, exactly corresponds to this value. When I sum this value and this value, I will get the amplitude of this function. And when I add this value and this value, I will get amplitude of this guy. And when I add this value and this value, I will get the amplitude of this guy. The phase spectrum gives me the information about the phase shift of these tones, of these harmonics. If there was no phase shift, these would be cosines. But because my phase shift here is minus pi over 2, those cosines are phase shifted so that they become sines. Here I will show you how to approximate the sum of the Fourier series that we computed in the previous slide in Matlab. So using Matlab, I want to approximately evaluate this infinite series. I can do it like this. First, I will define that the capital T is 1, which is my period. Then I will define this vector of times for which that Fourier series will be evaluated. This vector will go from 0 with the step of 1 millisecond all the way to the twice the period of the signal. Now Matlab is mostly numerical environment, so I cannot sum up infinitely many numbers. I can let this index k go only from some finite negative number to some finite positive number. Specifically, I will let the k go from minus capital K to plus capital K, and I will set that capital K to 200. So this index k will go from minus 200 to plus 200. Thus, I will only get an approximation of this sum. Now I will define the coefficients of my complex Fourier series. These are the coefficients. That means that I will take this expression and write it here in the Matlab language. Notice the use of this dot notation and this dot notation. This is necessary for this power and this division to be the element-wise operations. If, for example, you leave out this dot, this will become matrix division, which will not end up well. Now, this expression is going to work as long as this k is different from 0. When k is equal to 0, we are going to end up with some garbage. To avoid that, I have this line here, which assigns number 1 to the vector of these coefficients when k is equal to 0. Now, before I attempt to approximate this sum, I will plot these coefficients as the amplitude spectrum. So here I open the figure 1, and here this command stem will do this plot. On the horizontal axis, I will be plotting my indices k, and on the vertical axis, I will be plotting the absolute value of my coefficients, that is the amplitude spectrum. These parameters are here to make that plot look nicer. This dot tells Matlab to put dots on the top of each of these lines. This line width with the value of 1.5 will make these lines thicker so that they are easier to see, and this marker size with value of 14 will make these dots bigger, so again they are easier to see. Here I am setting the limits for the horizontal and for the vertical axis. These two commands will move the vertical axis to the origin of this plot, otherwise the Matlab would draw it here. This command will turn on this grid in the plot, and this command will turn off the frame that Matlab likes to draw around each plot. And last, this will label the horizontal axis, and this will label the vertical axis. So this is how I will get the plot of the amplitude spectrum of my signal. I'm just plotting the absolute value of the coefficients which I have defined here. Now what about the approximation of this sum? Well, that I'm doing here. First, I will define this vector x that at the end will hold that approximate sum of the Fourier series. At first, I will initialize it with 0, and its dimensions will be the same as the dimensions of this vector of time. Now, in this cycle, I will start to add up this sum. This cycle will go through all the elements of the vector c, that is through all the coefficients of the Fourier series that we have defined here, and in each iteration it will multiply one of those coefficients with the respective complex exponential, exactly the way it is done here. So in each iteration, this, which corresponds to this, will be added to my vector x. So in this cycle, I will approximate this sum for this index k going from minus 200 to plus 200. Here I will plot my result. So first I will open the second figure, that is this one, and then using this command I will plot my signal x. On the horizontal axis I will be plotting the time, and on the vertical axis I will be plotting my signal x. This command real is here to eliminate numerical problems. If everything is done properly, the result of this sum should be real. It should not include any imaginary part. But due to the imprecisions of the arithmetics in the computer, there may be some very small imaginary leftover in this signal x. This command real will remove any imaginary residual, and it will leave us only with the real part of this signal. This additional parameter line width with the value of 1.5 is there just to make the line wider and so easier to see. These commands are used just to format the plot, and they have the same meaning as the commands here. So when we execute this, the result is this. And you can see that this result is getting fairly close to the original signal. There are some deviations, as there should be, because I'm not summing from minus infinity to plus infinity. My k goes only from minus 200 to plus 200. If I increased this range, my result would be even closer to this original signal. So this is how you can approximately compute the sum of the Fourier series in Matlab. In this problem, I still want to find the Fourier series, amplitude spectrum and the phase spectrum of this signal. But this time I'm not going to evaluate any integrals. I could if I wanted to, but this signal is very simple, so I can save myself some trouble. This is just a cosine. That means that it is just a pure tone at a single frequency, at this frequency. So obviously this signal is going to contain only one frequency, this angular frequency omega naught. But how can I directly write this cosine in the form of a Fourier series? Well, I need to realize that the Fourier series expresses the signals as the sum of complex exponentials. So I will need to turn this cosine to a sum of complex exponentials. And from the previous lecture, we know how to do that. This cosine can be written in this form as a sum of two exponentials. And this expression I can write like this, which actually already is a sum of the Fourier series of my signal. Check it out. If this is the fundamental angular frequency of my signal, then I can also write it as 2 pi divided by the fundamental period of my signal. So this expression will be actually the same as this expression when k is equal to 1. So this entire expression will actually just be this element for k is equal to 1. Thus, this is the coefficient of the Fourier series c sub 1. Now what about this guy? Well, that is the same story, except now here I have this minus, so this complex exponential will correspond to this complex exponential for k is equal to minus 1. Thus, this entire expression will be this summand for k is equal to minus 1. Consequently, this is the coefficient of my complex Fourier series for k is equal to minus 1. So the coefficients of my Fourier series are going to be this, that is this, when k is equal to 1, and this, which is this, when k is equal to minus 1. And because this expression and this expression are the only two summands that are being summed here, when k is neither 1 nor minus 1, these complex coefficients have to be 0. So these are the coefficients of my complex Fourier series of this signal. Now what about the amplitude and the phase spectrum? Well, the magnitude of this and this is a over 2. So this is my amplitude spectrum for k plus minus 1. And because the magnitude of 0 is 0, my amplitude spectrum will be 0 when k is different from plus or minus 1. Now the phase spectrum. The phase of this is phi, that comes here. The phase of this is minus phi, that comes here. And the 0 can have any phase, so here I have chosen 0. Both this amplitude spectrum and this phase spectrum are plotted here. And from these plots you can read that our signal contains a single tone, a single harmonic at a single frequency. These two lines correspond to these two exponentials, which, when summed, will give us our cosine, our pure tone at a single frequency. And the height of these two lines, this a over 2, corresponds to the magnitude of the complex amplitude of these two complex exponentials. So 2 times the height of these two lines will give us the amplitude of this cosine. Or I can also say that when I add this value and this value, I will get A, which is the amplitude of this cosine. Now in the phase spectrum, I can read this phase phi, which is the phase of this complex amplitude, and that is also the phase of my cosine. So when in the spectrum I have two lines like this, that means that in the time domain I have a cosine. The amplitude of the cosine is given by the amplitude spectrum, and the phase of the cosine is given by the phase spectrum. Now, let's take a look at something a little bit more complicated. Again, we want to find the Fourier series, amplitude and phase spectrum of this signal. This time, I do not have a single cosine, but I also have this sine. How will I deal with this? Well, I could start integrating, or I could start thinking. First, I will note that the frequency of this sine is twice the frequency of this cosine. That means that one of the periods of this sine is going to be the same as the fundamental frequency of this cosine. Thus, our signal will be periodic with this fundamental angular frequency. The fundamental period we can get from this expression. When we express t, we will get this formula, and when we substitute 2 for omega, we will get that our fundamental period is pi. So when we take the general expression for the sum of the Fourier series and we substitute pi for t, we will get that for our signal we can write the Fourier series like this. Now, what are these coefficients of my Fourier series? Well, we will use the same trick as before. I will write this cosine as the sum of these two exponentials, and I will write this sine as the difference of these two exponentials. Now, this expression I can write like this, and this entire expression I can write like this. Here I can identify that this is actually this exponential for k is equal to 1, thus this entire expression will be just this summand for k is equal to 1. Consequently, this is the coefficient c sub 1. Here I can see that this is this exponential for k is equal to minus 1. Thus, this entire expression is this summand for k is equal to minus 1. Consequently, this is the coefficient for k is equal to minus 1. Here, this exponential is actually this exponential for k is equal to 2. Thus, this entire expression is this summand for k is equal to 2. Therefore, this is the coefficient c sub 2. And finally, this exponential is this exponential for k is equal to minus 2. Therefore, this is the coefficient for k is equal to minus 2. Now, I will take these coefficients and I will summarize them like this. This is the coefficient for k is equal to 1, that is this coefficient. This is the coefficient for the k is equal to minus 1, that is this coefficient, and so on and so forth. And just like this sum contains only these 4 coefficients. So if the k does not have one of these 4 values, the coefficient is 0. Now, what about the amplitude spectrum? Well, that is easy. The magnitude of this complex number and this complex number is 3, so the amplitude spectrum will be 3 for k is equal to plus or minus 1. The magnitude of this complex number and this complex number is 4, so the amplitude spectrum will be 4 for k is equal to plus or minus 2, and the amplitude spectrum will be 0 otherwise. Now, the phase spectrum. The phase of this complex number is 1, so that will come here. The phase of this complex number is minus 1, and that will come here. Now, to get the phase of this complex number, I first need to write it in the proper polar form, which I have done here, and from here I can read that its phase is 3 minus pi over 2. So here I can write 3 minus pi over 2. Now, to get the phase of this complex number, I again first need to write it in this proper polar form, and when I do that, I can read that its phase is minus 3 plus pi over 2, and that will come here. I can assign any phase to 0, so here I chose 0. So finally, this is the phase spectrum of my signal. Now, this amplitude spectrum I plotted here, and this phase spectrum I plotted here. And here, these two lines correspond to this cosine, and from here I could get its amplitude, and from here I could get its phase. And these two lines correspond to this sine, and from here I could get its amplitude, and from here I could get its phase. But here I have a warning. This is the phase of a cosine that is phase shifted so that it corresponds to the sine. Therefore, this value, that is this value is not 3, it is 3 minus pi over 2, because when you take a cosine and you phase shift it by minus pi over 2, it will turn into a sine, which is what we have here. So when you see two pairs of lines in your spectrum, that means that you have two tones in your signal. In this case, we have the first, the fundamental harmonic, and we have the second harmonic. This is the fundamental harmonic and this is the second harmonic. In this slide, we still have the same task. We want to find the Fourier series, amplitude spectrum, and the phase spectrum of this signal. This time, the signal is equal to time in the interval from 0 to 1, and it is periodic with period of 1. So this is what my signal looks like. It is this sawtooth signal. Now let's start crunching. There is no funny stuff that I could do with the integration interval. I will just integrate from 0 to 1 and I will integrate t. I will integrate this t. So this integral will turn into this one. And this integral I can evaluate per part. I will be integrating this exponential and I will take derivative of this t. So I will get this. Here I have integrated this exponential, and here I copied this and I took the derivative of this t, which turned into 1, so it's no longer here. Here I need to be cautious, the omega k must not be 0, therefore this will be valid only if k is different from 0. Now in this expression I will substitute these limits and I will also substitute for the omega sub k. The omega sub k is equal to 2 pi k over the period and my period is 1. So this will turn into this. When I make the substitutions, this expression will become this one. Here I can note that the phase of this complex number is the integer multiple of 2 pi. Therefore, this complex number will be equal to 1. Thus, this entire expression will become this one. Now, this integral I can easily evaluate into this, and when I substitute these limits, I will get this. And here, when I substitute 2 pi k for the omega sub k, I will again get a complex number with phase that is the integer multiple of 2 pi. Therefore, this complex number will be equal to 1. This is also equal to 1. Therefore, this entire expression will be 0 and it will go away. The only thing I'm left with is this expression, which I can also write like this. I must not forget that this is valid only for k different from 0 because I cannot divide by 0 here. For k equal to 0, I can compute the coefficient c sub 0 as the average value of my signal, and just by looking at this picture I can see that it is 1/2. Now when I use these values of my coefficients, I can write the Fourier series of my signal in this form. These are the coefficients, this is the complex spectrum of my signal. When k is different from 0, the complex spectrum is this, which comes from here, and when k is equal to 0, the complex spectrum is 1/2, which comes from here. Now the amplitude spectrum. The magnitude of this complex number is this, and the magnitude of this complex number is this. Therefore, this is the amplitude spectrum of my signal. Now the phase spectrum. This is a purely imaginary number, so when k is positive, the phase of this complex number is pi over 2. When k is positive, my phase is pi over 2. But when k is negative, this number will have negative imaginary part, therefore its phase will be minus pi over 2. When k is 0, this is just a real number, so the phase is 0. Here, the amplitude spectrum and the phase spectrum are plotted. This line corresponds to the average value which I have plotted here. This pair of lines corresponds to the amplitude, and this pair of lines corresponds to the phase of the first, the fundamental harmonic, which I have plotted here. This pair of lines corresponds to the amplitude, and this pair of lines corresponds to the phase of the second harmonic, which I have plotted here. And this pair of lines corresponds to the amplitude, and this pair of lines corresponds to the phase of the third harmonic, which I have plotted here. And so on and so forth. Here I have the fourth harmonic and here I have the fifth harmonic. When I add this average value and these 5 harmonics together, I will get this signal. And you can see that this signal already starts to resemble my original signal. If I edit all the harmonics, this signal would approach this one.